Thanks for coming in, Mr. Riemann. Welcome to Göttingen. I want to know all my new students, and so, please take a seat. Tell me about yourself. I'm all ears.
Hi, ma'am. Please call me Bernhard. Yeah, sure thing. Well, where do I start?
Well, let's see. I see in your files that you grew up in a poor community. Tell me about that experience.
Sure. Well, I was born in Hanover. Parents were Lutheran pastors. And I'll admit, life growing up was tough. I had an older brother, 4 sisters, lots of mouths to feed with not enough money.
Wow, that's really interesting. What about your education then?
Honestly, not the best. I mean, I was homeschooled till 3rd grade, and I eventually ended up studying math and other subjects at Lundberg, where the director took me in. And that really got me into math, even though my family wanted me to do theology or whatever. But that's the reason I'm studying it. But I plan to switch over to math eventually, but we'll see.
Okay, well, that tells me a lot about you. I just know you're going to do great here in Göttingen. Nice to meet you, Bernhard. I know it's a short talk, but definitely one worth having. See you around. Bye. Riemann, it's been what, 13 years?
Oh my god, it is so good to see you. I cannot believe you're still here. Anyway, I'm here for business. I want a job here.
Really? You want a job here? Didn't you study with Einstein and Gauss, even Dirichlet? You must be a math genius now.
And I made a lot of major breakthroughs while I was gone. And oh yeah, trust me, I worked with them a lot. I know you probably don't know exactly what I'm talking about, but I'm going to tell you anyway.
No, please, tell me.
I'm just messing with you. But okay, seriously now. I worked with a lot of complex variables and non-Euclidean geometry, but all that aside, I worked extremely hard with Gauss and published my first paper recently. Let me tell you, the concept I created will change math forever.
Okay, listen. I know some math, but not that much. Could you please explain?
Sure. I call this the Riemann Sum. Simply defined, it's the approximation of an integral by a finite sum. We use this technique to approximate the area of functions or curves on a graph.
No way! Please tell.
Oh, absolutely. Let me show you on this paper here. Look, take a look. All right, let's do the Riemann Sum. Now, when I created this formula and this concept, I've created 4 variations of it. The left Riemann sum, the right Riemann sum, the midpoint Riemann sum, and the trapezoid Riemann sum. But for sake of your time and my time, let's do the left Riemann sum. So, the formula, officially, reads like this. Delta x is the interval, and this is the height of whatever rectangle we're going to create. Now, let me explain the concept regardless of the formula because I know it can be a little bit scary. Let's use a regular function. Let's say f of x equals x squared plus 1, right? If I sketch a graph of it real quick. And I make my points, let's say 2, 4, 6, 8, 10. And I make let's say just 1, 2, and 3, right? Let's say, I think roughly the graph would look something like this. Right? Let's just say it's like that. Might not be the most accurate, but it's fine. We'll get the job done. So, realistically, the concept is used to do the following. We're going to determine the approximation under this curve for any set or finite sum. So let's say we want to determine the area from points 1 to 3 under this curve. We could use the Riemann sum to do that. So, how do we do that? What we can do is we can decide a set number n, which you see here, as the amount of rectangles we want to create under this curve, each one being of the same interval delta x. So let's say we choose 4 in this case, right? We'll go 1 here, 1 here, one here. So that's 2 rectangles that we have right now, and obviously we need 4. So the next 2 points we would need would be 1.5 and 2.5, right? And as you can see, now each rectangle is separated by a width of 0.5, meaning delta x is equal to 0.5. Now based on this formula, we can now calculate the sum from 1 to 3 under this curve. So we start off with the height of the rectangle. So the first rectangle, and I forgot to mention this, I apologize. We're doing a left Riemann sum. And so the left Riemann sum is done from the left corner that touches the curve and then goes across to complete the rectangle. So from here, we start at the left the left point, which is at the curve, go across. That's our first rectangle. Our second rectangle goes from here to here, the second rectangle. Third rectangle goes from here to here. And our fourth rectangle goes from here to here. As you can see, these are the 4 rectangles that we have. So for our first one, our height is approximately around 2, right? 2 times our interval, which is 0.5. Or rather, we can say our height times our interval, or delta x. So we can continue across. First rectangle was 2 times 0.5. The next rectangle was a height of, let's just say 3 for the sake of convenience, times our interval, which stays the same as 0.5. Next rectangle was at around 5. So we can do 5 being the height again, times our interval, which is 0.5, standard. Finally, our last rectangle, which was at 6. 6 times 0.5. And now, this addition and multiplication will give us the sum of the area from point 1 to point 3. Let's do it. 2 times 0.5 is 1. 3 times 0.5 is 1.5. 5 times 0.5 is 2.5. 6 times 0.5 is 3. So 1 plus 3 is 4. 1.5 plus 2.5 is 4. We have 4 plus 4 equals 8. Hence, the total sum under our curve from point 1 to point 3 is 8. This is the left Riemann sum. If we were to do it with any of the other variations, there would be a slightly different tweak, but this is all we have time for. Thank you.
Wow, well after seeing all this, I can truthfully say that your mathematical brilliance surely surpasses all the professors we have right now. Welcome on board. You're going to be our new head of mathematics. We're all gathered here today to honor the life of Bernhard Riemann. He was a mathematical genius who revolutionized the course of mathematics. Unfortunately, Riemann passed away due to chest pains and tuberculosis last night. But today, we are gathered to honor the man who gave us models that redefined space, gravity, time, and laid the foundations for Einstein's theory of relativity. It is due to him that we are gifted with the Riemann's zeta function and his unsolvable hypothesis. We will now have a moment of silence.